All right, so we'll go ahead and get started. The Karst Waters Institute would like to welcome you to the first in a series of seminars that we're calling the Frontiers in Karst Colloquium. And we're starting this out with a series of presentations on the theme of carbonate critical zone processes. And we're doing this in collaboration with the Carbonate Critical Zone Research Collaboration Network that was recently funded by NSF. And we're going to start out with 3 talks this fall, one per month this fall, which you can see here on the slide. And then we plan to have 3 more talks in the spring. And at that point, we will decide whether we want to continue forward with the series, perhaps choose a different topic. So we're also, we welcome input on ideas of speakers or ideas of things that we might do in this space in the future. So our first talk in this series is going to be by Dr. Xiaoli Dong, who got her undergraduate BS degree at Zhejiang University in biological sciences. And then she continued on to a PhD at Arizona State in environmental life sciences. And that was followed up by a postdoc at Duke University, where she began to do the work on the depressions in Florida, which she'll be talking about today. And then just in 2018, she started as a new assistant professor at University of California, Davis. And without any further delay, I would like to welcome Xiaoli.
Okay, should I start my share screen here right now?
Yes, you can go ahead and do that, and I'll stop to make sure that it lets you do it.
Okay, I think it's up, right?
Yes.
No, it's not. Let me do it. I need to start over. My computer's not working. Okay, this should work. Okay.
There we go.
Let me just hide this. Okay. Thank you everyone for attending my talk, and good morning, good afternoon, good evening, depending on where you are. What I'm going to talk about is the work that I did at Duke when I was a postdoc there. I was working with Jim Heffernan and Brad Murray. So these are the co-authors on these papers that I'm going to present. The project was funded by NSF, and the project was led by Matt Cohn from University of Florida. Okay, this is the landscape I'm going to talk about. This is Big Cypress National Preserve, located in South Florida. What you are seeing here is a landscape that has like these green mounds embedded in it. And these green mounds are called Cypress depressions or Cypress domes. They are evenly spaced with each other, meaning that they are not randomly distributed, they are not clustered. The distance from one depression to another depression is about the same across the whole landscape. So that is really mysterious. And this NSF project was proposed to answer this big question, which is what is going on? What causes this even depression across the whole landscape in Big Cypress? Okay. Before we go on to talk about Big Cypress, I'd like to just mention a little bit about my own research program. So I'm not an expert in karst at all. What I do is that I focus on ecosystem spatial patterns, in particular self-organization. I'm very interested in the spatial self-organization of ecosystems. So what you are seeing here in these 4 pictures are some examples of ecosystem self-organization. So one characteristics that's shared by these 4 examples is that everything looks regular. So on the top left, it is the termite mounds, that these green dots are termite mounds, and they are evenly spaced across the whole landscape. On the right, these are various circles. Each circle is a bare ground, and then they are embedded within a grass matrix. And these circles are evenly spaced. Then on the lower left, these are the ribbon forests. The space in between these forest lines are even. On the right, it is a soil profile you are looking at, and these red lines are the oxidized iron, and you can see that these red lines are evenly spaced across each other. So this is a project that I started to collaborate with when I was a postdoc at Duke with Dan Richter, to try to understand at what kind of soil profiles can we see this kind of evenly spaced redox patterns, and at what depths of the soil, and can these kind of patterns emerge, and its relationship with hydrology. So that's the central focus of my research, and in particular in this talk, I'm going to talk with you about the project that I worked on as a postdoc at Duke. So the site is located in South Florida, and so here's Big Cypress, and this is Everglades National Park. What you are seeing here on top here is the Lake Okeechobee, and then in the wet season, there's water flowing across this whole landscape. So there's the surface water covering this whole landscape. The landscape is very flat. The global relief, the overall landscape relief is about 0.5%. So it is really flat. There's a lot of regular patterns on this landscape. These are depressions, and these are the ridge and slough patterns in the Everglades. If you've never visited there, I strongly recommend you go see it. It's really beautiful. So let's take a zooming view of this, the landscape of the Big Cypress. So these are some Google Earth snapshot of the site. So this is Big Cypress. You see these gray dots that's embedded in this green matrix. These gray dots are the depressions, and let's zoom into to see what they look like. These are the shape of them are circular, and in some of them you see this kind of opening in the center of it, and I'm going to talk about that, what happens to that. And each depression is about 50 to 70 meters in radius, and the distance from this one depression to next depression is about, I guess it's like from 60 to about 120 meters, depending on the location of the particular patch in the site. So it gets this name, Cypress dome, because of this dome shape of the feature. So you see that the trees on the edge these are cypress trees. The trees on the edge is shorter than the ones in the center of it. And in fact, it seems that the reason that the trees on the edge are shorter is not that they are younger. It is mostly because the ones on the edge are more water limited than the ones in the center. So you might be wondering why there's water limitation in Florida. It receives like 2 meters of rain every year, right? And so let's look at the cross section of this cypress dome. First is that you get this dome shape at the above ground, and then underneath it is actually depression. So we call it Cypress depression or Cypress dome, depending on whether you're talking about above ground or below ground. So below ground is depression, and this whole landscape is located on karst limestone bedrock, and most of the places it's exposed limestone bedrock. In some places, there's some shallow soil cover. The center of the depression is usually about 2 meters, and it's covered by about 70 to 80 centimeters of the soil to 1.2, 1.3 meters in the center, and there's water, standing water in the center of it. And one thing that I want to mention, which is really important, is that there's strong seasonality in terms of the precipitation in this system. So that's why it's water limited, because there's a very long dry period in South Florida. And so during the dry period, some of the water can dry out, and the trees on the edge is going to be water limited. And so this is showing you what it looks like in the center of a depression. So the standing water mat is standing right in water in the center of a depression. First, let's look at the pattern, just to see whether they are actually regular patterned. We did a bunch of statistics, spatial statistics, to analyze whether these depressions are actually evenly spaced from each other. And the answer is yes, it's statistical significant. These depressions are not random, not clustered. They are over-dispersed or random, over-dispersed or evenly spaced or regular. So these terms means the same thing. Now the question is why? Okay, so I'm just going to show you the roadmap for this talk. We address this question, which is the mechanism of this pattern, from 3 spatial scales. The first scale is at the soil bedrock interface scale. At this scale, we were interested in this question how old is this landscape, and what process created this kind of pattern? So we built a reactive transport kinetics model to try to answer that. And then the second scale is at individual basin scale. In this scale, we build a 3-dimensional basin genesis model. The question we are interested at this scale is what kind of process and feedback controls the size of individual depression. Then moving on to the third scale is at the landscape scale. At this scale, we are interested in the causes of this over-dispersion of the depressions on landscape. And we use a third model, which is a landscape evolution model. So this is what I'm going to talk about, start off at the first scale, which is at the soil bedrock scale. Okay, so the idea behind this project is that, so we want to know how old is this landscape. What that means is that when did this depression forming process start on this landscape? And so we know, so how do we figure that out? We know that in the center of the depression, in most of the depressions, it's about 2 meters. So if we can figure out the mean annual weathering rate under the condition of South Florida, then we have put these 2 numbers together. We can figure out approximately how old this landscape is, right? So now the only thing we need is this weathering rate given the condition of the South Florida. So we start off with this weathering model. There are 3 rate limiting processes in limestone weathering. First is the input of the CO2 and the conversion of the CO2 to carbonic acid. This is a relatively slow chemical reaction process. And then the second process is the dissolution of the limestone. And then the third limiting process is output of the export of the weathering products. You need to move those calcium out of the system once the limestone is weathered. And in all these processes that you see, it involves water. So we need to get the hydrology of this system right. So there are 3 key hydrological states in this system. The first is in wet season, the whole landscape can be covered by surface water. So in that state, all the depressions are hydrologically connected. Then water level is going to decrease, and you will see that there's still surface water in the center of the depression, but these depressions are isolated from each other hydrologically. Then moving further into the dry season, in some places, the surface water, even within the depressions, can completely dry out. So these are three stages of hydrology in this system, and they are super important for weathering rate. Also, not only to these three steps that I mentioned, but also to the movement of the CO2, the transport of the CO2 in soil profile. So let's look at this governing equation of the CO2 movement in soil profile. I'm just going to walk you through. Some of you might be very familiar with this, so just bear with me. So there's three terms here on the right side of the equation. First is the diffusion of the gas CO2, and then the diffusion of the dissolved CO2. And the last term here is the advection term, which is the CO2 movement with the liquid water. Let's look at these two parameters here in the diffusion of the CO2. There's the diffusion coefficient of the gas form and dissolved form. Notice that in the diffusion coefficient in the gas form is about 4 orders of magnitude higher than in the dissolved form. So what does that mean for weathering? The process of weathering needs acid. In this particular case, the acid is CO2. So CO2 comes from either atmosphere or from the root respiration, right? And so as you move from left to right, what you're looking at here is the soil profile, soil moisture content. And as you move from left to right, the soil is drying out. So the soil water content is decreasing. When that happens, means there's more airspace in soil. So more CO2, a larger proportion of CO2 is going to leave the soil profile through the upper boundary into atmosphere instead of moving downward to the soil bedrock surface interface for weathering. So that leaves less CO2 for the weathering process. And the second process here is advection. Advection here is basically moving of the CO2 with water flow. And water flow is usually from going downward direction, right? Driven by gravity. And so we have two terms here, which is elevational head and pressure head. And elevational head is moving, usually the direction is moving downward to the soil bedrock surface. But when soil dries out, this pressure head is going to be driven by very strong capillary. And so this advection rate is going to decrease over time when soil dries out. At some point, when soil on the surface part is really dry, this arrow can even change direction, change from downward to upward. So when that happens, that more CO2 is going to move upward rather than downward through advection. So you can see that when soil dries out, less and less CO2 gets moved downward to the bedrock surface for weathering. So we need to get the hydrology right in order to get the weathering rate right. And so we built this model that has 4 modules in it. First is we have the soil transport process in the model, and then we have the chemical kinetics, and then we have the hydrology that includes all the process that such as precipitation, runoff, evapotranspiration, etc. And then we have the biology, which is basically we are very interested in how much CO2 that root respiration is producing to feed the weathering process. So this is a biological term that's represented in the CO2 governing equation. So these are the 4 modules in the model. What we need from this model is this one number, which is the weathering rate. And we get that weathering rate, we put the number with the depression, the depth of the depression, and we get the age of the landscape. What we found is that the landscape, the pattern generating process started about 10,000 years ago. So that is about at the end of the last glacial maximum when sea level rise, when sea level is high enough that it goes approximately to the surface of the bedrock, and so the system can start to hold surface water, because otherwise when the seawater is too low, then the surface water is going to go downward, and the system will not be able to support the surface water. So, and when the surface, at that time, the system started to get more wet and then can support all these cypress trees. And there's pollen record showing that when the cypress trees start to move into the system. So we used actually three very different methods to estimate the age of the landscape. So this is a model approach. Then we use also a mass balance approach, and there's also geological dating. So these three methods all point to approximately same magnitude of number in terms of the age of the landscape, approximately about 8 to 10,000 years old. Okay, so that's the answer to the first question. But use this model, we can look at a lot of other things. For example, we can look at how weathering rates are changing as a function of a set of variables, such as annual precipitation and groundwater drainage rate. So let's just zoom in to look at a few of them here. First, what you are seeing here is the weathering rate as a function of the annual rainfall. So weathering rate will increases and then start to level off. What you are seeing here, this solid point is representing South Florida. Then the second variable here is the groundwater drainage rate. When the groundwater drainage rate increases, it will accelerate weathering rate because the groundwater drainage provides a pathway to export the weathering product. But if the groundwater drainage rate is too fast, then the system is losing water faster, and that's going to shorten the hydro period for a system. That's going to limit weathering rate. So you start to see declines. And the last two plots that I want to show you here is the effect of the biology on the weathering rate. So the one on the left is showing you like more loot and faster weathering rate, which is straightforward. And then on the right is showing the effect of the architecture of the loot on the weathering rate. So if you have shallow loots, that's going to lead to a slower weathering rate just because the distance from the loot zone to the bedrock surface is longer. So you lose more CO2 to atmosphere rather than moving downward. So we did a global sensitivity analysis of the model to see within this, like dozens of the variables, which of them are most important for weathering rate. So the top four that come out is, so the way you read this figure is that everything that's more towards the upper right are more important. So the top four here are basically the precipitation and the biology-related variables, such as loot mass and loot architecture, and also the soil thickness, amount of the soil cover on top of the weathering, the front. So for this particular landscape with the with kind of vegetation there and with climate there, we found that in Big Cypress, the biological respiration accelerated the limestone weathering about 20 times. So what does that mean? What that means is that if, let's assume that the cypress trees were never there, and after 10,000 years, what we would have is not the big cypress depressions that we see right now. Instead, the landscape would look like limestone pavement after 10,000 years of depression of the weathering. So this process where biology accelerating weathering rate and creating this depression types of morphology, this whole phenomenon, we coined this word called ecological gel hypothesis. Okay, so this is the end of the first project where we figured out how old this landscape is and what kind of process are influencing the weathering rate. Now let's move on to the second scale, which is at individual depression scale. At this scale, we want to know how a depression developed from a very tiny limestone pit to what it is right now and what is the future going to be like. Is it going to keep expanding in its radius and become all connected eventually? Or is it going to become deeper and deeper and at some point become cenotes everywhere in South Florida? Or is it going to stay the way it is because the system is already in equilibrium? So these are the set of the questions we are interested in at the second scale. Now let me just give you some intuition about the kind of feedback that involved to answer this set of the question. So as a depression develop from a small pit to what it is right now, more trees are going to start established inside the depressions, right? So as tree grow, it provides more CO2 from root respiration as well as soil respiration from decomposition. And that's going to accelerate weathering. And so with higher weathering, the basin is going to expand faster in their size. And when basin is bigger, it's going to hold more water. So the hydro period is going to be longer. And so with longer hydro period, that's going to be a positive feedback on the weathering rate. So this is a positive feedback here. At the same time, with more water in the depression, it's going to also facilitate the growth of these cypress trees. So they are less water limited. So this is a set of positive feedback, but there's also negative feedback. So now with more water trapped inside of depressions, let's assume that the total amount of the water that goes into the system stays the same over time, which is a big assumption given the scale of the time. But let's just assume that with more water that get trapped inside depression, less water is going to be on the upland matrix. So landscape inundation period is going to be shorter. What that means is that that's going to limit the export of the calcium. And if the weathering product can't be exported, that's going to be a negative feedback on the weathering rate, right? So this is a negative feedback. So we build a model that includes all these processes. We build hydrology into the model with the precipitation, surface runoff, and groundwater exchange. And then we build biology in it, which is basically very naively represented by just the growth of the tree with logistic function. And then we have the soil accumulation basically coming from the two major processes. One is the weathering product, insoluble mineral left by the weathering. And then the second is the organic matter built up by the roots. And then the third process is the limestone weathering. And these are a set of the laws that we extracted from the first model. So these are the key modules that we built in this three-dimensional basin genesis model. And what we found is that, first is that the landscape right now is far from equilibrium, at least at the individual depression scale. In fact, the depression is it is almost at highest level right now. So this is what you are seeing here on the y-axis is basically the weathering rate, and this is where we are right now according to the model. And the radius of the depression on average is about 50 meters. In equilibrium, it's going to be about 80 meters. The depth is right now about 2 meters. In equilibrium, it's going to be about 7.5 meters. What that means is that by the time when the individual depressions stabilize, the total depression area is going to increase from a quarter of the landscape to 60%. Oh, I forgot to mention, so the depression, according to the model, these depressions are going to stabilize at in about 200,000 years from today. So then the next question is, okay, well, they will eventually stabilize. They are not at equilibrium yet, but what are the feedbacks that's actually involved in stabilizing the landscape, and which of the feedback is most important? Okay, so we looked at 3 different types of feedback in the model. The first one has to do with evapotranspiration. So this is the landscape again here. You see 2 types of the patches. The gray patches are the Cypress depressions, and these green patches are pine trees. So we call them pine tree upland. So the ET rate is a little higher in the depression patch than in the upland patch. So let's just look at the mass balance. So if the depression area increases over time, we would find that the mean landscape ET is going to increase over time too, right? And let's assume that the amount of the water that's provided to the system stays the same. With more water leave the system through the pathway of ET, less water is going to leave the system through surface drainage and groundwater drainage. And that's important for weathering because surface water and groundwater are actually doing the weathering, provide the condition for weathering to happen. It provides wetness that's needed for weathering. It provides ways to export weathering products. So if more water is leaving the system through ET, then you would expect that the overall weathering rate is going to reduce at landscape scale. So that's the first negative feedback that can stabilize the depressions. The second feedback has to do with the soil thickness. So this is the depression, and this is the bedrock soil interface where weathering is occurring. And over time, the amount of the soil is going to increase on top of this weathering front. And what we found from the first model, and which is also supported by a lot of literature, is that the amount of the CO2 that that gets moved to the bedrock soil surface is going to decrease as more and more soil covers up on this, basically as the thickness of the soil cover increases. So that means that less CO2 is available for the weathering at the soil bedrock interface. So this is another negative feedback. The third negative feedback has to do with biology. So you've seen this figure already, that these several variables related to biological process really stand out in influencing the weathering rate. So we, from the model, we see that in equilibrium state, the center of the depressions can get to 7.5 meters. So 7.5 meters is really deep. There's no way that these cypress trees are going to be able to still live there, right? So the trees are going to die. And also the seeds recruitment rate is going to decrease as the water gets deeper and deeper, right? In fact, in some of the big depressions on the site right now, you start to already see this kind of openings in the center of the depressions. And if you go inside check, you will find the openings are created by the mortality of the tree. A lot of the cypress trees start to die in the center of it just because the water is too deep. So at some point, the national park is going to change the name of this place from like Cypress Depression, Big Cypress Depressions to Big Cypress Donut, something like that. Okay, so these are 3 feedback, and then we use the model to explore which of these feedback is most important in stabilizing a system. What we do is by just turning off on and off different feedback to see the sensitivity of the depression stabilizing process to that feedback. What we found is that the most important feedback is the soil cover feedback. So it plays a biggest role in stabilizing landscape, and followed by the biological process, which has to do with the tree growth and seed recruitment. And the ET feedback is does not contribute that much to the stabilizing the depression size, and that's understandable because the ET rate difference in ET rate between the 2 patches is not great. Okay, so I told you that the depressions, according to the model prediction, they are going to stabilize in about 200,000 years. And a lot of things could happen within this 200,000 years. One thing is obvious is the sea level rise, and in fact, it's projected that by the end of this century, there's going to be about 3 to 4 feet of increase in the sea level rise in that region. And what that means is that probably by the end of the century, if not, definitely in the next 200,000 years, the Big Cypress Depression, the Big Cypress National Preserve is going to be under the seawater. So yes, the system is going to stabilize at some point, but they are going to be probably be under the seawater. Excuse me. So in fact, it has been, this is really interesting. This kind of patterned landscape, karst landscape, has been observed on the seafloor in some places. This is a study from the Red Sea and Arabian Gulf. What they found is that there's this kind of patterned depressions on the karst under the seafloor, on the seafloor there. So what you are seeing here is not a model result. This is actually the real topography on the seafloor. And so this might be something, this might be a morphology caused by the process that we are seeing right now in Big Cypress, even though what we have is still above the sea water. And there's this news coming out, I think it was in 2018, and off the Alabama coast, on the seafloor, about 20 meters below the sea level, they found a big forest of cypress trees there. And these cypress, according to the data, they found that these, according to the dating, these cypress trees were they were about 50,000 years old. So, so is it possible there might be some kind of pattern landscape there? We don't know because we don't have the morphology data in that site yet. I don't know whether we have right now after 2 years. Okay, so that's the second project at the individual depression scale. Now let's move on to the last project at the landscape scale to answer the question of the over dispersion of these depressions. Let's go back to these self-organized regular patterns. And I would like to introduce you this concept called self-organization, which is the general framework to understand this kind of regular pattern, spatial patterns on the landscape. It comes from a paper published in 1954 by Alan Turing. What he was interested in at that time was, is there a general framework that we can use to explain those regular patterns that we see on animal skin? And so in this seminal paper, The Chemical Basis of Morphogenesis, Alan Turing came up with this mechanism called scale-dependent feedback. So let me show you what this means. Using an ecological example, okay? So scale-dependent feedback means that in a short range, it's positive feedback, and in long range, it's negative feedback. So let's assume in a water-limited system, there's a tree, a bush, growing in this point here. So x-axis here, the distance. So the tree is growing in this 0 point. And it's going to modify the soil there, and it's going to take the water and from the nearby area and modify the soil texture so that the water retention in that area is going to be higher, and the tree can grow better in that point, and so it can take in even more water. So this is a local positive feedback. But if the whole system is water limited, if this point the tree is taking up more water, that means that the area nearby it is even more water limited, such that the second plant will not be able to grow there. Instead, the second plant can only grow outside of this zone of the negative influence by the first plant. So if you repeat this process in space, you get a regular pattern. And this process is called scale-dependent feedback. And it is a mechanism that is used in a lot of models and papers to explain the regular patterns observed in all kinds of ecosystems. So is this, we can also apply this mechanism for big Cypress. Let's just replace this tree with the Cypress domes. So remember this system is water limited, right? It has a long dry season. So during that period, if there's a big depression here, the water level is going to be lower compared to a small depression for two reasons. Obviously, first is if the depression is bigger, it's deeper. So water level is deeper. The water level is going to be more water there. But at the same time, because the biomass density is higher, meaning that the evapotranspiration is going to be also a lot higher, then the water level is going to drop faster. So this bigger depression is going to be a sink of water, and it's going to suck water from the nearby area and moving to feed this big depression. And so it's going to suppress the growth of the smaller depressions in this zone of the negative influence. And the second depression can only grow in a place which is far enough away from the first depression. And then if you repeat this process in space, you will expect a regular spaced depression pattern. So this is our first hypothesis, which is a scale-dependent feedback mediated by subsurface water flow to explain this even spacing. The second hypothesis that we come up with is from geomorphology, and which it has to do with competition among catchment. So in geomorphology, we observe that these kind of regular spaced ridge and valley patterns, and that comes from the competition among two catchment for catchment area. So catchment area here is an proxy for water. So each catchment is grow according to its own set of the rows, and then there's the watershed divide. And as each catchment grows, there's an adjustment of this watershed divide as a result of a competition between two catchments. And eventually you will get these kind of evenly spaced ridge and valley patterns. So this is a mechanism from geomorphology, has to do with competition. So we built a model, a landscape evolution model that incorporates these both mechanisms, the scale-dependent feedback and the competition mechanism. And we want to know which one is actually contributing to this pattern formation in big Cypress, or both of them are. So what we did was we turned off the competition mechanism. When we turn that mechanism off, we found that we don't get circular depressions. Instead, we get this kind of labyrinth or network type of patterns. But if we turned off the scale-dependent feedback, we find that these kind of evenly spaced depressions still emerge from a homogeneous initial condition. Except that the size of the depression does not match what we observe here. So only when we have both mechanisms turned on can we get both the pattern and the size of the pattern match up with what we observe. So what we conclude here is that the pattern in big Cypress is the spatial patterning, the spatial arrangement of the patterning is controlled by the competition among depressions for catchment area and the size. But in order to form this pattern that perfectly match what we observe right now, we need both mechanisms to operate. What you are seeing here is just a set of the result from model compared to the empirical observations. And what's really interesting, I want to point out here is that the last two plots here, over time, we found that the regularity, the regularness of the patterns increases. So at the beginning, it's regular, but it's not that regular. But over time, you see that the pattern gets even more regular. Okay, and this kind of mechanism have been observed in other type of ecosystem too. What you are seeing here is the evenly spaced fairy circles in Namibia, and what they found is that it is the operation of the both scale-dependent feedback and competition among termite mounds that create this evenly spaced fairy circles. But here competition means something completely different. This is biological competition here. Okay, so that's the end of the third project. Just very quickly, I want to talk about this region in general. There's a lot more patterns in South Florida than the Cypress depressions. So these are Cypress depressions. In some places, the Cypress depression actually takes on this kind of eardrop shape and align with the flow direction. And then we get the ridge through pattern, and we have tree island pattern. So there's a pattern transition. So if you look at this bottom row of the pictures here, this west part is big Cypress depressions, and moving towards the east side is Everglades. This kind of pattern transition occurs within like a few miles. So the question is, what is going on? Why pattern moves from this kind of weathering pattern to this kind of depositional pattern? So this is the peat accumulation here in the east. And so these are the questions that's not answered, and we are building a model to understand this kind of pattern transition right now. Okay, so that's the end of my talk. Thank you for your attention.
All right, so thank you, Xiaoli, for the very thought-provoking talk. The way that we will handle questions here is I've just opened up the chat so that people can type questions into the chat. If you have a question, then type it in, and we'll read it off and we'll discuss some of those. While we're waiting for the first questions to come in, I'll go ahead and take the opportunity to ask a question. So I'm curious about this concept of equilibrium and the growth of the depressions. Mm-hmm. Normally when I think about equilibrium, I think kind of a balance between two things, let's say, that might shrink or grow the depressions.
Yes.
But in your case, it's the negative feedback that's sort of making the growth slower and slower and slower. Mm-hmm. So I'm curious, how is it you were defining the equilibrium state?
Oh, that's an excellent question. Okay, so two things I want to mention. First is that this line here, you can still see my screen, right?
Yes.
Okay, yeah, okay, so this line here that I showed you when I talk about equilibrium, it's never goes to zero. So it's just asymptotically goes to zero. So it's the negative feedback that slows down it, and it never actually goes to zero. Second is that you mentioned that when we think about equilibrium, it's always two opposing forces. One is expanding, another is shrinking it. So what is the thing that's shrinking it? In this particular case, there's actually a process that's shrinking the depressions, which is upland weathering. So think about it. If we have depression embedded in upland, and if we keep the depression the same, we assume there's no weathering in the depression, and the upland keep weathering, then the depression eventually is going to disappear. So the weathering of the upland is the shrinking process for depressions. But for this particular case, because a lot of times in a year, the upland is dry, so the weathering rate in the upland is really slow, but it's still a process that can shrink the size of the depression. Does that make sense?
Yeah.
Yeah, thanks.
Okay, so now I have confirmation that the chat actually works because I'm seeing questions appear. I'll read the first one, and then I'm going to alternate with Rachel Bosch, who's a PhD student who's also involved with the Karst Waters Institute. Okay, so John Martin asks, could the transition from Big Cypress to Everglade type patterning be related to average elevation of those landscapes relative to sea level in the region? If so, is it possible to preserve a patterning such as in Big Cypress as sea level rises and floods those areas?
Yeah, okay. Okay, there's several things going on here. First is that, yeah, so that's a hypothesis that we want to test, which has to do with the elevation of the landscape. We know that the landscape is very flat, but in South Florida, but there's still elevational gradient, and Big Cypress is higher than Everglades, and so in fact, there's water flowing from Big Cypress to Everglades, and so the dry period in Big Cypress is longer than Everglades. So the first hypothesis that we are testing right now is just whether it's the difference in the hydro period that's caused by the elevational difference is the process that caused the transition from the depression, the weathering type morphology to depositional type morphology. Okay, so that's what we are thinking right now. And in terms of the sea level rise, well, I think if we just consider sea level rise in terms of the wetness, it seems like, according to all these models, suggesting that if our hypothesis about that the transition caused by the hydro period is right, then yes, if there's more water, then it's going to transition from the Big Cypress to Everglades, except if this kind of system is initial condition sensitive. So what that means is that if we give the Big Cypress what we have right now to give the condition what we have in the Everglades to Big Cypress, so put the Big Cypress system under the condition of the Everglades, does this system still have the potential to change from the weathering system to the peatland system? We don't know, because some of the this kind of morphological development is very initial condition sensitive, and so that is only considering seawater as hydrology, like influencing hydrology, but then we also know that seawater is going to change the chemistry. And so what does that do to weathering? I don't have a straightforward answer, but I think it's like this is the set of the questions that we are testing right now. I don't have the answer, but I would really like to, have discussion about these kind of questions.
Okay, thank you. Our next question is from Logan Schmidt, and it is, why aren't all water-limited karst landscapes characterized by evenly spaced depressions?
Well, that's a great answer. Okay. So okay, so the paper is going to, in the landscape evolution model, we actually explored a set of initial conditions that, can influence the development of the landscape, and such as like the bedrock surface roughness. If the bedrock surface roughness is too high, you won't see this kind of landscape anymore. I mean, as an initial condition, if the roughness is too high, and also the local heterogeneity in terms of the elevation. If the local heterogeneity is too high, you won't see this kind of depression, evenly spaced depressions. And so it seems that according to our landscape evolution model, the emergence of this kind of landscape also depends on the initial condition. And also notice that it also depends on the kind of the biology there, right? And if we don't get the cypress trees there, you won't see these kind of depressions. As I showed you, it's going to be just limestone pavement. So we discussed this set of the conditions for these kind of depressions to emerge, and I think the paper is going to come out soon. I'm going to when the paper come out, I will send the reference to this Karst group if possible. Can we move on to the next question?
Okay, yeah, I had to unmute myself. Okay, so the next question is from Lee Floria, and he asked a question which is actually kind of related, which is, to what degree does the antecedent topography in the Everglades from variation in depositional facies contribute to modern landform patterns? So again, thinking about initial conditions, but specifically the facies.
Like what, I guess I don't quite understand, like what depositional phases, what does that mean?
Yeah, so thinking about like the changes in the rock texture and porosity and properties because the rock is formed in different depositional environments across that area.
I see. Yeah, I don't have. I don't know that because I've been looking up like literatures to know more, to understand more about like the geology of the South Florida, like in terms of this kind of bedrock formation, like try to figure out what it was like for this bedrock when they were initially formed, and whether there's some kind of significant difference in terms of this depositional phases in the bedrock in these two areas that could lead to the differences that we observe right now in these two systems. And how can we translate that to a set of cascading process that lead to the big difference that we have right now? But to be honest, I don't know the answer to this question. This is a question I've been thinking about and try to like construct the logical flow to connect like what we had in the initial condition of the bedrock in Everglades and in Big Cypress to what we have now. And I don't have that flow yet, so I don't know.
Okay, the next question is, what is controlling the initial distance between the depressions, and can this be predicted based on the precipitation rate?
When you say initial condition distance, do you mean the initial distance between the depressions in the initial condition of the landscape? I don't understand. What do you mean by initial? If you can clarify, what do you mean by initial distance?
Yeah, Piotr, you can also unmute yourself if you want to clarify your question.
Yeah, sure. I would like to clarify, you know, when we look at those photos, they are really amazing how equally distanced those depressions are. Mm-hmm. So if I told you what is the precipitation rate in Florida, could you predict that the distance between the depressions will be, say, 60 meters? I mean, is there a formula for this? I'm just curious about this.
Okay, great. Thank you for asking this question. That's also a scenario that we explored in the landscape evolution model. What we did was that we manipulated a gradient of the annual precipitation in the system from even more limited, water limited than it is right now in South Florida, to like all the way to just annual precipitation such that the whole system is covered by surface flow all the time, perennially. We found that the two things change along this gradient. First is that if I push the system to more water limited, the pattern become more regular. And if we make the system completely not water limited, the system is not regular anymore. I mean, the depressions, the spacing of the depression is not regular anymore. So that's one, the spatial arrangement is changed. Second is the distance. The distance has to do with annual precipitation too. So when you reduce the precipitation, the distance increases. The distance between the depression increases. that's what we found using the numerical experiment with our model.
Okay, so we'll take one more question. It's 6 o'clock, so we should probably wrap up. But or 6 o'clock my time. I think it's different times for everybody. But so the final question is from Young Li Gao, and he wants to know: would extreme events such as hurricanes disrupt the landscape pattern and eco-hydrological equilibrium?
Well, that's a really, really interesting question. I've been wondering about that. It's these are some things that you wonder about when you have too much time during pandemic and just, take a walk again and again. Yes, so this is a question that we are thinking about, but we don't have the answer. Certainly, like a system that the kind of like precipitation we put in the model is just like it's contemporary annual precipitation pattern. We certainly, the model is at annual scale. We do not include all these extreme events, but we would assume that one easy link that I can think about is that the hurricane is going to influence like a landscape pattern through its influence on the biology, which is the like if you disrupt the ecosystem, biological ecosystem there, that's going to influence the weathering rate. Another thing that I want to mention, which is not what you're asking, but related to this kind of extreme events is the fire. What we found in the second model, which is the basin scale model, is find that this fire is also important in this pattern formation. In this particular system, we find that if there's no fire in the system, the soil is going to fill up the depressions. So if the organic matter that's built up in the depressions are not burned, the soil accumulation rate seems to be high enough to fill up the depression. So what does that mean? That means that if the depressions get filled up, then there's no surface water that can be held in the depressions. Then that means that the cypress trees would not selectively grow in those depressions. Then that means that the depressions, this kind of even over-dispersed landscape would not emerge. So like, it was kind of like strange to see this kind of connection, like from fire to this kind of morphological development of the landscape. Okay, that's the answer.
Okay, I have one last question for you. You were describing how these depressions would look in the equilibrium condition that emerged in your modeling, where you have the deep water in the middle and the trees dying off in the middle. And so my question is, would this equilibrium be something that has to emerge kind of system-wide simultaneously, or do individual depressions reach an equilibrium state? And, if so, are there any that you would say are now at equilibrium, and can you measure that in the field and see those?
Okay, so a quick answer is no, they don't reach equilibrium. They don't reach equilibrium simultaneously. The reason is that what we found is that the weathering rate is slow at the beginning because there's no tree growing there, and then you start to have water and then cypress tree coming, and then it's going to accelerate the weathering, and then weathering rate going to slow down. It's kind of logistic curve. So what that means is that a little bit difference in the size of the initial limestone pit, those like little holes, the initial little difference in the size of that hole is going to make a big difference after like a few thousand years in terms of the size. So some depressions are definitely like a lot smaller than other depressions in the landscape. We don't see this kind of donut shape in all depressions, only some of the really big ones that you see tree dying in the center of it. So that's the answer to your question. At the depression scale, at the landscape scale, through that competition mechanism in the landscape evolution model, we find is that we also see that the depressions are at different stage, reaching equilibrium, but we see that because the big ones that eventually is going to slow down their weathering rate, right? So the smaller, relatively smaller ones keep expanding. So that's why we see that over time, that the size gets more even across the whole landscape, and the distance among the depressions also gets more even over time. So that's why the whole system, both in terms of the size and the spatial configuration, gets more even over time.
Okay, great, thank you.
Thank you for all the questions. These are really interesting questions.
Okay, so thanks again, Xiaoli, for a great talk, and thanks to everyone for showing up today for the first of the Karst Waters Institute Frontiers in Karst Colloquium, and we hope to see you at the next one next month.
Thank you, Matt.
Yeah, bye.
Bye.